Kruger, software architect at DataFlint, who will be talking about optimizing Apache Spark tasks. So Marais, I hope I'm pronouncing your name right.
Yep, very good pronunciation.
Amazing. Okay, great. Proud of myself. I will let you take it from here.
Okay. Hi, I'm Marais. So basically, what we do on a high level at DataFlint is we bring in the production data and tell you how to use the production data in order to optimize and save costs. Go to the next slide. Okay, so what we're going to cover now is a scenario where you have airflow with airflow DAG, and you have a couple of Spark operators in there, and you want to find how can you reduce your cost. And I'm going to go through 3 basic questions, and so what I'm trying to bring to you is how to bring visibility to what happened in your Spark cluster during the execution of your different airflow tasks. So we're going to go through question 1, which step is eating your budget, and identifying the hotspot. Question 2 is, should you run these steps in parallel, or is it better to run it sequential? And it's not always that intuitive. Sorry, just go one back. I want to say the last one. Okay, and then and lastly is, do we utilize our allocated resources that we have during this Spark execution? Okay, go ahead, next slide. So finding the most expensive step. So we have a scenario that ran in the automotive industry, and what we do at DataFlint is we take the tags, which is provided by the Airflow operator, which provides us the data, the tag ID, the data run ID, and the task ID, and we have visuals about the run and what happened inside the run. So this is a visual representation that we have in our platform that represents what happened. So what we provide here is the timeline. You can see it's similar to what you have in Airflow, but what we add here is the more metrics that you have for the Spark, the input volume, and we do a cost estimation based on the size of the cluster and the utilization of the job, how much CPU and memory that it uses. What else? Yeah, I can go to the next slide, please. Okay, so in the previous slide, we could see which steps caused the highest cost, and then the next thing that you should do is then understanding, okay, why is it costing us? Why is this step costing so much? And finding the root cause in one of the scenarios was that we saw that the same for each step in each Spark session, five identical data reads was done, and causing a 6.25 billion rows read that was unnecessary. And if you look at the visualization that we provide in our enriched Spark, then you can see that after the filter, you have only 500K rows. And so the fix was to make a single line change and do a cache after the filter, which made you only read the files once and save a lot of cost. And these are very easy to fix problems, but it's not so easy to find them. And the way we pop them out so you can easily find them is we have different what we call alerts. And one of them is what we do is a repeated lineage to see that like the same lineage happens over and over again. We do it by doing graph hashes, like the Weisweiler-Lehman hash, that will immediately detect like duplicate sections, pieces in a graph, and point it out and make it clear that there's a cache opportunity. And also, of course, we look at the size that you're able to cache it. Next slide, please. Okay, then the next question I want to address is, should you run your tasks in parallel or sequentially? And the answer is not always clear what you do, but there are some guidelines that I want to present here. So we had a scenario in one of our clients where we had job B and job B report. That was the critical path that was detected. And during this critical path, there was 3 other jobs or runs that was competing for resources. And one thing to always remember when running Spark is that Spark is relatively memory hungry when it comes to executing things like sort. And so if you have a memory hungry operation like that, and you have competing resources, what will happen is that you will see that that you will easily go into disk spill, and Spark, if it can't sort it in memory, it goes to the external sorter, which starts running the sort operation on disk instead of memory, and can slow down the whole Spark job by a factor of 10 or 100 sometimes. And so in this scenario, it was better to run it in sequence so we can get better usage of our resources, to change the steps to run sequentially, improved and added a lot of cost saving for this particular scenario. Next step, please. And then another question to answer is, okay, so you define your cluster and you give it X amount of resources. Now the question is, are you using your resources? And this is not so easily visible if you use the standard Spark UI. What we provide is insights, which we divide into 3 measures, which we call demand, supply, and use. So demand is saying to the executors how many cores you want. So that is typically in Spark language. It means how many partitions you have, because that is the parallelism that you have in Spark. So if your demand is way under the supply, then you're not going to utilize it. So in this particular graph, you can see that supply cores is in orange. You have 100 cores, and the demand is in green, is way lower than 100, and this is very bad utilization, very poor utilization of your CPU and your resources. And the blue is, of course, the used, what is actually used. So we use these type of metrics to make decisions on how to optimize your Spark application. And you can go to the next slide, please. So continuing the resource utilization. So what we also provide is now in Spark, you can have in a single application different queries if you're on a DataFrame API. So these green bars are the queries, and what you see on top is the running cores and the amount of executor cores. So in DataFlint, we capture this data. It's not available in a native Spark. We capture extra information to show you what is the running task, actual task that was scheduled and that's running in that particular moment in time, and map it to exactly which stages and which queries run. So in this example, you can see in the bottom query that a lot of the time that it's that in its lifespan, there's a curve that goes down, and you see it plateaued to 1. I happen to know it's 1, and now the question is, why is that happening? So in the next slide, if you would click on that particular query, you will see what happened during this query. And queries in Spark is divided into stages. And what we show on the right side is which stages ran in time. As you can see, some stages ran in parallel. But by visualizing this example, you can see that there seems to be a problem during stage 55, which is a long one, which takes a big chunk of the idling number of cores. You can see that it's using like a very low amount of cores. So the next step is the okay. Now we identified the stage that's potentially a culprit. Let's go and drill into the stage. So you go to the next slide. You will see, okay, this is what's happening inside the stage. Now again, this is metrics that we collect that is not available in the regular Spark, which is telling you exactly what happened. If you see in the left diagram, you can see that your task went up and then it went gradually down. And if you can see there the label, it's showing it only one task ran for the rest of the duration. And you can also see that we show quantiles, like that you can see like the longest task took 13 minutes. And this is a typical signature of a partition skew. And so by now looking at this whole story, we identified that, okay, we identified which query, which stage, and why is the stage not utilizing the cores. And if we can go to the next slide, please. Okay, so now if you drill into that particular stage, in the query plan of the physical plan of the stage, you will see in this example that it's doing a join. And the one side of the join is 44 gigabytes, and the other side is 32 megabytes. And this shows you that like it's not the primary reason that there is a skew, but it makes it apparent that there is an easy way to fix it. And one of the ways to fix it is to say, okay, let's broadcast a small data frame, and then you won't have a shuffle at all, and you will get rid of the data skew implicitly. And that's it for this slide. I'll go to the next slide. Okay, so to summarize, so what we do is we propagate all the Airflow metadata and add a lot of Spark application metrics to it and give you a better visual of what happened underneath the hood and what happened in time. We attach the cost to the Spark to the Airflow run and the Airflow step or task. We give insights into the Spark physical plan, where we do lots of sophisticated alerts. We're taking into parallelism of different stages that ran in the same time and understanding if it was really underutilization. And all of this, what I just showed you, is not actually it's not actually the product. The product is all of this context information hooks up to the MCP server, where we can hook it up to your favorite LLM, which gives production insights by seeing your source code and understanding what happened in during the run, and provide you, and the LLM gets much more intelligent in understanding how to fix your potential bottlenecks. Then the last slide. So what I presented here is the SaaS application, but if you want to get started with DataFlint, we have an open source product, which is easy to set up. So if you would create a Spark, the only thing you have to do when you create a Spark session is you need to add our DataFlint Spark jar and specify the plugin. And then magically you'll see another tab appear there in the regular Spark UI, and from there you'll see some of the things that I showed you today. And this is free, and you can go and have a play with it today and check it out. Next slide. And that's it. Thank you.
Thank you so much, Marais. It looks like you have a question in the chat from Vikram. He says, is this a typical scenario of CPU versus memory utilization or purely an example?
This is a typical scenario. So if I'm referring to the parallelism versus sequential execution. So a rule of thumb is like if you have CPU, if you're running tasks and they are low on memory, it's okay to run in parallel. But if you have different runs that is memory intensive and causing contention for the same resources, it's better to run in sequentially. I hope that's so. Actually, it's not just an example. These are real world examples that I showed you. So I hope that answers your question.
All right, thumbs up from Vikram. Great. So